Welcome to the Deep Dive. Today we're getting into some really interesting agricultural tech. Think about this. Your crucial field data may be getting skewed by just a tiny shift in temperature, like 1 degree. That's sort of the hidden challenge we're digging into. I want to unpack how this specific sensor, the crop circle ACS470, which is really customizable, can be improved, and how these small calibration changes can really mess with your results if you're not careful. So yeah, let's dive right in.
Absolutely. It's a core problem, really. Getting accurate plant data out in the field, it's tough. Conditions change. And temperature swings, they're notorious for messing with sensor readings. So yeah, we're looking at how you can get reliable, high-quality data despite all that.
And this crop circle ACS470, what makes it stand out is that you can actually customize it, right? With those 12.5 millimeter filter options. And it has manual normalization, which sounds great for research, really targeting specific light wavelengths. But I guess that flexibility adds complexity too.
It definitely does. Fundamentally, the sensors inside these silicone diodes, they're just naturally sensitive to temperature. It's physics. Their electrical output changes with heat. We've seen it even a 1 degree Celsius rise can shift readings by, say, 0.24%. But here's a really important bit, the nuance. Different filters on different detectors within the same sensor unit, they can react differently to the same temperature change. It's not uniform. Think of it like different components having their own quirks.
Okay, so if even small temperature changes cause these variations and different parts react differently, how do you manage that in a real field environment? Seems tricky.
That's the million-dollar question, isn't it? And that's where this white panel method really becomes, a bit of a game changer for us. We use these large standardized white panels made of titanium dioxide and hold the sensor at a set distance, like 1.2 meters. It gives us a stable, known reference to measure against.
Right, so it's about creating a standard baseline check.
Exactly. It lets us standardize how the sensor performs, and importantly, it shows us the basic signal noise level for each individual detector. It also helps figure out how the different bandpass filters affect the signal coming in. And get this, some filters, like a red 6 nanometer 1, might cut the raw signal down by like 95.5%, an NIR 800 millimeter filter, maybe 99.7%. That's a huge reduction, so the tiny bit of signal left gets amplified a lot in the final reading. Any tiny instability gets magnified, you see. So this method lets us characterize each detector individually. We see some values go up with temperature, some go down, some might even flip behavior. Each sensor filter combo has its own sort of unique performance personality.
Wow, okay. But here's where it gets even trickier, right? Even if you calibrate perfectly before you start, things can change during data collection. You're saying you might do a check after being in the field and find the detectors aren't reading that white panel correctly anymore. They've drifted. Off by 1% or even more.
Yeah, precisely. That drift is a real issue, especially for calculating things like NDVI, the normalized difference vegetation index. That's a super common metric for plant health. Now imagine your red detector drifts. Maybe its reading increases by 0.4% for every degree Celsius rise, but your near infrared, your NIR detector, drifts the other way, maybe decreasing by 0.3% per degree. That difference, it compounds. It creates a bias in your NDVI that's not real, it's just sensor drift. I actually know of a case where someone collected data all day, seemed fine, but months later their analysis just wasn't matching ground truth. Turned out, temperature drift skewed their NDVI all along. That's why you absolutely have to characterize the thermal drift for your specific detector setup. You can't use a generic correction. And we really suggest using the white panel readings themselves, before and after, as the main basis for correction, not just relying on temperature logs alone.
Okay, that makes a lot of sense. So for someone using this kind of tech, what are the key practical steps? The takeaways to get better data. Well, first, give the sensor a good long warm-up. Let it stabilize thermally. We're talking maybe 30 minutes, maybe even up to 3 hours. Second, think about insulation. Something simple like Mylar bubble wrap can actually help buffer the sensor against direct sun or wind, keeping its internal temperature more stable. Helps it maintain maybe 10-20 degrees C above the ambient air temp, but more consistently. Third, always do that white panel normalization, that unity check, before you start collecting field data. And this is crucial. Do it again right after you finish collecting. Take both pre and post field measurements. That way you can actually see if drift occurred, how much, and potentially correct for it.
Exactly. Look, the ACS470 is a solid piece of equipment. It's robust. But following these kinds of enhanced protocols, that's what really unlocks its full power for serious research. It turns that raw data into insights you can truly rely on.
So what does this all mean for you listening? I think the big message is, next time you're working with sensor data, pause and think about the potential invisible factors. It's not just about what you're measuring out there in the environment. It's also about tiny shifts happening within your tools. And this deep dive really shows that sometimes getting the clearest picture means meticulously understanding and accounting for those hidden variations in your measurements. That's how you turn data into dependable knowledge.